as a consequence of the Riemann-Roch theorem, another notion we will introduce will be the Weierstrass semigroup. But before explaining what it is, let me begin an observation which says that in a given function field of genus G, if we consider a place and if we consider a natural number which is bigger than 2 times G, then we can guarantee the existence of a function which has pole divisor exactly NP. And to see the existence of such a function, we will consider the Riemann-Roch spaces of the divisor n minus p and the np. Since n minus p is less than or equal to np, always we have this inclusion. And our claim is that this inclusion indeed proper. So that means we are able to find an element in this space which does not lies in the F space of n minus p. And first, let me see that this is a proper inclusion. Indeed, we will argue that by using the dimensions of these F spaces, and we compute the dimension by first observing the degree of these two divisors, and the degree of the NP, n times p, and always degree of a place is bigger than or equal to 2 because it is defined as the extension degree of the residual class field over K, and this is always bigger than n, and by the assumption we know that this is always bigger than or equal to 2G minus 1. And similarly, we can also observe that the degree of these divisors is also bigger than or equal to 2G minus 1. Then by the consequence of the Riemann-Roch theorem, since their degree are sufficiently large, they are large enough, we get the dimension of L minus P is its degree plus 1 minus G, and the dimension of the divisor NP is n times degree P plus 1 minus G. And since this quantity is always less than or equal to, always strictly less than this one because of this degree P term, by the dimension argument, we see that indeed this inclusion is proper. So that means we can choose a function in NP, but which does not lie in the Riemann-Roch space of the divisor n minus p. And indeed, by the definition of the Riemann-Roch spaces, and by comparing the two divisors, we can see that Z has a pole at P of order. And this shows us the pole divisor. So there exists a function whose pole divisor is exactly NP. So, okay, if n is sufficiently large, we can find a function which has pre-described poles. However, there can be also, there can be also some natural numbers which can gives us this proper inclusion. And If this is the case, we call this natural number a pole number of the place P, or equivalently, we can also say that if there exists a function whose pole divisor is NP, and otherwise, so that means if we have equality between these two Riemann-Roch spaces for a natural number n, then we called n a gap number of P, or we will also say that n is a gap at P. For the pole numbers, let me give an observation. If we have two pole numbers n and m, of a place P, then by their definition, we know the existence of the functions f, x and y that have pole divisors as np and mp. And now our claim is that indeed their sum is also a pole number of the same place P, because we can see the existence of the function as a multiplication of these two functions, which is the pole divisor as a sum of mn mp. And this shows indeed in this, if you fix a place and if you consider the all pole numbers, they are closed under addition. And there are also natural numbers. Depending on this observation, we introduce a notion to represent pole numbers of a given place, and we denote it by W of P. And such a subset of n, which is also closed under addition, will be called Weierstrass semigroup. And we can also see that this summation satisfies associativity. So this is why it is called semigroup. And depending on their notions, now in general, if we have a function field, which is genus G, and if we are not in the rational function field, then if this function field also contains a rational place, let me denote it by P, then Indeed, we will see that genus gives us information about the number of the gaps at this place. In other words, then there are exactly G gaps at this rational place. And let me denote them by I1, I2, and IG, which have increasing order with initial term 1 and the last gap number is bounded below the 2G minus 1. For this theorem, let me do some observations. For instance, let's check if the natural number 0 is a pole number of P. And indeed, we only apply the definition of being a pole number, so that means we check this to Riemann-Roch spaces has proper inclusion. For n equal to 0, we want to see that a space of the minus P properly lies in a space of the zero divisor. Indeed, this is true because it has negative degree, so this is a trivial space, and trivial space always properly lies in the base field K. Our second observation will be 1 is a gap number of P, or 1 is a gap at P. And similarly, we check if these two Riemann-Roch spaces are equal to each other. When n equal to 1, so in this case, we know it has positive degree and the dimension will be bigger than or equal to 1. So to see this equality is not so that trivial, and this is why we prove it by contradiction. So let me suppose towards contradiction, let me suppose indeed L of 0, so the full constant field lies in the H space of LP properly. And in this case, that means there exists a function there is a non-constant function which is bigger than, or its principal divisor is bigger than or equal to minus P. So in this case, since P is a rational place, is of degree 1, this negative term, and this is a non-constant function, contains P, and indeed we see that pole divisor of X is indeed P. And if we consider the extension of the rational of our function field over the rational function field K of X, here the X is denotes the transcendental X we pick from the LP, we know that this extension degree is determined by the degree of the pole divisor of this transcendental. And since this pole divisor is equal to the rational place, it has degree P. It has degree 1. And we get our function field as a rational function field. It has also, by the assumption, we also suppose that it has degree 1. Indeed, this shows us the genus is 0. But it contradicts by our assumption. So in this case, A space of the zero divisor must be equal to the Riemann-Roch space of the rational place P. And this shows us when is a gap at P. And to decide to other gap and pole numbers, it's quite natural to consider the chain of Riemann-Roch spaces, which is determined by the multiples of the rational place P. And as we observed that we have equality here, and we want to understand for which step, for which chain we have equality or we have proper inclusion. At least when, as a consequence of the Riemann-Roch theorem, at least we can observe that if n is sufficiently large, so that means if it is bigger than or equal to 2g minus 2, it's possible to compute their exact dimension. In this case, it's degree n plus 1 minus g. For instance, if n is 2g minus 1 here, we get the dimension as g. And for the remaining terms, so if you consider the Riemann-Roch space of the divisor, the consequent divisor n plus p, in this case it's degree plus 1, n plus 1, plus 1 minus g, and if you plug in 2 minus g for n, we see that it has dimension g plus 1, so we get this strictly increasing dimension. And this shows us after the n term, when as n is bigger than or equal to 2g minus 1, we always have pole numbers because of these proper inclusions. So for natural numbers which are bigger than or equal to 2g minus 1, we know that they are pole numbers of f. So that means there is no gap after this n term. So that means if you want to conclude something about the gaps, the interval we should check should be between the S space of the zero divisor and S space of the 2g minus 1p. And this shows us indeed the last term of the gap numbers can be at most 2g minus 1. And when is also a gap, as we have observed here, this shows us the first gap number should be 1. Now, to see that there are exactly g gaps, so that means there are exactly g many equalities, so we have already observed the first one. We want to understand how their dimensions are related. And first, let me observe that dimension of the quotient space regarding this chain, regarding the I term, is bounded below the difference of their degrees, and in this case, it is going to be 1. So the dimension of divisor IP is bounded above the dimension of the previous term plus 1, and it's also bounded above dimension of this previous term. And this shows us the I term, the dimension of the I term, since the difference, since this is an integer and this difference is 1, we can conclude that this dimension is either equal to this one or the other one. And thanks to this observation, indeed, we can see that there are exactly, if we don't count the first one, there are exactly G minus 1 equality between the dimensions. So that means there are exactly G minus 1 numbers between 1 and 2G minus 1. Which has this proper inclusion. And the remaining G numbers are subset P. And all of has the jumps of length 1 and we get the proper inclusion. If you want to use it, if you want to represent it in a fancy way by using the notation of the Weierstrass semigroup, in that we can also see that its difference from natural numbers gives us the genus G. So this is also, I mean, in the research, this topic is also investigated. I mean, people are looking at the Weierstrass semigroup and its properties and their structures. In this course, we are not going to consider in this direction. We are not going to consider this direction. But for the moment, I just want to give brief explanation. For instance, if genus is 1, and if we have a degree 1 place, so that means we will see that in elliptic curves, the natural number 1 is the only gap number of P, and its Weierstrass semigroup is determined by the natural numbers without 1. And in general, if we have a function field f over k, and if the characteristic of the constant field is 0, and if we have, of course, the rational place, it's Weierstrass semigroup in general determined by the natural numbers depending on the genus and depending on the genus plus 1 consequently. And for the genus which is bigger than or equal to 2 and k is algebraically closed, of course, this Weierstrass semigroup structure depends on the places we consider, but it is known that almost all places have the same Weierstrass semigroup. But here the almost makes us skeptical because it has been also observed that there are some exceptions, but finitely many exceptions. So there can be finitely many rational points which don't give the same Weierstrass semigroup. And such points or such places are called Weierstrass points. So if you are interested in this direction, particularly in the relation with the coding theory, we will see that later to construct some algebraic geometric codes, we will consider Riemann-Roch spaces. And in this case, if you pick a Weierstrass point P, and if you consider the divisor of Kp when K is small enough, This structure in general is useful in the construction of the algebraic geometric codes. However, in this course, we are not going to go, we are not focused on this direction. And on Thursday, as an application of the Riemann-Roch theorem, we will consider the strong approximation theorem as a stronger version of the weak approximation theorem, and we will conclude the consequence of the Riemann-Roch spaces. So see you on Thursday. Bye-bye.